Okay. Alright, so let's continue our discussion on chapter 35. On the last online lecture, we discussed on the effect of energy activation in the Arrhenius formula. So we discussed based on the kinetic notes that I posted on the blackboard. So if the idea here is that for a reaction to take place in an elementary reaction, it requires a collision, right? So this collision is a function of average velocities of the gas molecules. I mean, it's quite intuitive. So the faster the average velocities of the gas molecules, then the more collisions frequency it has. Okay, so the frequency of collisions of two gaseous molecules of the same kind is proportional to its concentration raised to the power of 2. Okay, so and also if the frequency of collision for two gases of a different kind, A and B, the collision frequency is proportional to the concentration of A times the concentration of B. Now you see this ratio or expression or term when we're describing a rate law. Okay, when we have a rate, generally for an elementary reaction of a reaction A plus B going to C, for example. So the rate is equals to the rate constant times the concentration of A times the concentration of B, and this order is 1 for each of the reactant. Right, this is for elementary reactions. So this means that the reaction is a second order reaction, right? And its molecularity, or the mechanism, is a bimolecular collisions, right? This is second order for bimolecular collision. Okay, so if this is an elementary reaction, so it means that it requires collision of A and B to start the reaction. All right, so then as we are talking about collisions, and we have established that collisions frequency is a function of gas velocities, and this velocity is expressed in this formula is a function of square root of temperature over the molecular mass. Okay. Now we discussed the example of decomposition of hydrogen iodide with a mass of 127.9 gram per mole at 500 and with a concentration of 10 to the power of minus 3 molar. Now if you calculate with the kinematic gas theory, the collision rate for these conditions is 3.5 times 10 to the power of 28, right? And if you divide by the Avogadro number, you will get the collision per molar per second to be 5.8 times 10 power 4. But at this condition, the reaction rate is still really small, 1.2 10 to the power of minus 8 molar per second. This is molar per second is rate, right? It's unit of rate. Now, if we compare the reaction rate over the collision rate, we are short by 10 to the power 13 times. So which means that the reaction rate is 10 to the power 13 times lower than the collision rate. So most of the collisions are not producing a product. Okay? Now, when we increased the just have a look here so that we can see on the screen. When we increase the reaction temperature to 510, increased by 10 degrees, the reaction rate increased by 44%, right? Now, when we checked with the average velocity, the increase in the velocity when you increase the temperature by 10 degrees is only 0.6%, right? So this cannot explain why the reaction rate increased by 44%, because when you increase the temperature by from 500 to 510, the velocity, the average velocity increase is only by 0.6%, which is really small compared to the increase in the reaction rate, which is 44%. As a conclusion, so the collision frequency alone cannot explain the large increase in the reaction rate. Okay. Now this brings us to the Arrhenius relation, right? So when the Arrhenius relation is the K reaction rate constant equals to the A pre-Arrhenius factor times E raised to the power of minus EA over RT. Now this E raised to the power of EA over RT is a fraction of molecules that has energy higher than the activation energy to decompose or to react, right? So if you make ln on both sides, this will be ln K equals to ln A minus EA over RT. When you vary the temperature, with temperature, and you plot 1 over T in Kelvin and versus the ln reaction rate constant, you will get a straight line where that straight line has a slope of minus EA over R. Okay. Right, and the reason for this increase, right, for when you increase 10 degrees, when you increase the temperature by 10 degrees and the reaction rate increased by 44%, the reason for this is that there are now more, if we have this plot of kinetic energy of a molecule, of molecules, and percent of fraction of molecules, or percentage of molecule, doesn't matter. So the molecule will have a distribution of energy at certain temperature, right? Let's say this is at 500 Celsius. Now at 510, you will have something like this, right? 510. Now, so the average kinetic energy, shifted. Obviously, if you have a higher temperature, then you have higher kinetic energy. The molecules move faster. But if this is our threshold or activation energy, right? If this is our threshold, when you increase by 10 degrees from 500 to 510, you will have more molecules that have that energy higher than EA, which means if you integrate the area under the curve at 510, you have more molecules that can overcome that energy activation barrier. So the order of the elementary reaction would be that of the stoichiometry of the equation. So the rate of this reaction would be reaction rate constant times the concentration of AB, the first reactant, and the other reaction C. Right? So every reaction has an activation energy barrier. So if you plot the energy profile of that reaction coordinate or reaction progress, first you have the reactant in this side, right, and then you have the product energy level on this side, and the difference between the reactant and the product energy level will give you delta G of the reaction, right? Now, in order for the reactant to go across to the product, it has to overcome an energy barrier, and this energy barrier is called the activation energy, right? So it must have to the molecule when the reactant molecules, when they collide with each other, it must have enough kinetic energy to overcome this barrier and to be in this transition state. And when it's here, it can decide whether it wants to go to the product side or go back, right? Okay, so and we have discussed that the reaction rate constant is a function of an Arrhenius a constant, pre-Arrhenius constant times the e raised to the power of minus EA over RT, right? R is a gas constant, and T is temperature in Kelvin, EA is the activation energy. So this term is the fraction of molecule that has energy higher than the EA, right? So let's say you have this plot, a plot of fraction of molecule versus the kinetic energy. So let's say this is at 500 Celsius. So if we, let's say hypothetically, we put this value as the value of activation energy. Okay. Then if we so you will have, then you will have this fraction of molecules that will have enough energy to overcome this barrier. So when you increase the temperature, okay, let's say by 510 degrees, then the number of molecule of the reactant that has energy higher than EA will be the area under the curve, which means that it's much more than the one at 500 degrees, right? Under this condition, when you increase the temperature to 510, you will have more reaction, or the reaction rate will increase, because the reaction rate constant increases, because as the temperature gets higher, this term becomes closer to 1, right? And as a result, K will be higher. Okay, so when you plot the Arrhenius in a linear way, this will be like this. You put ln here, okay, and you plot ln K, reaction rate constant as a function of 1 over T, Kelvin minus 1, and you will have slope, negative slope, in which the slope is minus EA over R. Okay. Right. So let's say the reaction is catalyzed to have a smaller activation energy. Okay. Let's say now there is another pathway where you use a catalyst, and the activation energy is slower. Now let's call this EAC, catalyze, right? So if it's slower, so which means that in this diagram the activation energy will be somewhere, let's say somewhere here, the new activation energy, right? EAC, catalyze. So in this case, you will immediately see that at 500, for example, you will have more molecules under the curve that has enough energy to overcome that barrier, right? So if you go back to this equation, if this becomes smaller, right, then this term will be closer to 1. Okay, this term will be closer to 1. You can make this term closer to 1 as a maximum fraction, as 1, either by increasing the temperature or making the EA smaller. Right. So